Good morning, Panthers. It is Dr. Augustine. How are you doing today? Today we are going to talk about reaction stoichiometry. And by that we mean using mass relationships within a chemical reaction. Now, the last topic we learned was about balancing chemical equations. Once you have a balanced equation, you have a really powerful tool for allowing you to predict how much products are going to be formed, and you can even go the opposite direction. If you know how much product was formed, you can actually go back and predict how much starting material you had. So this is a super powerful tool. It's sort of what most people remember about chemistry is the ability to measure mass and mole relationships in a chemical reaction. It all depends on a balanced equation. All right, so let's use the simple analogy of something that's near and dear to all of our hearts. Well, I don't know all of our hearts, but many of our hearts, and that is pizza. Who doesn't like pizza, right? So this is a nice picture of cheese pizza. Hopefully you're not getting too hungry looking at that. And cheese pizza in a really simple formula could be something like 1 crust plus 4 ounces of pizza sauce plus 2 cups of cheese yields 1 pizza. And that could be your balanced equation. And here's the key to this balanced equation. You have a ratio out in front of all these different ingredients to make your final pizza. So there's 1 crust for every 2 cups of cheese, 4 ounces of pizza sauce for every 2 cups of cheese, and 4 ounces of pizza sauce for every 1 pizza. So we can use a reaction if we say, what if we have 8 cups of cheese? And we have more than enough of all the other ingredients. How many pizzas could we make? We can set up a ratio of 1 pizza for every 2 cups of cheese. And this right here is the key step. This is called the stoichiometric ratio that comes from the balanced equation. So this stoichiometric ratio is going to be the key thing we're going to talk about here. It comes from the balanced equation. So we have a balanced equation. We have the ratio between the different ingredients. That shows up as a conversion factor and lets me figure out just how many pizzas can I make. Now look, you're really smart. You can figure this out easily by yourself. You see cups of cheese, cancels cups of cheese, and this is going to tell me that 4 pizzas can be made. All right, we can do this with any relationship. We can say, what if we have 15 crusts? That's easy. 1 pizza for every 1 crust. Crust cancels crust. We have 15 pizzas are possible. Now, in the next section, we're going to talk about what if we don't have the exact correct amount. That's called a limiting reactant problem. We're not going to deal with limiting reactant problems in this video. We're just going to deal with if we have enough of all the ingredients. So if we had 15 crusts and 15 times 4 ounces of pizza sauce and 15 times 2 cups of cheese, we could make a total of 15 pizzas. All right? Let me just reiterate the key idea here then. These numbers out front in my balanced equation, remember they're called the coefficients. These coefficients out front are the key to coming up with this term right here or this term right here. That stoichiometric ratio, which is the thing that tells you how the things are related to each other, how these different reactants are related to each other. All right, you've used this with cooking before. Now we're going to use this with chemical reactions. All right, so before we proceed to an actual example problem, let me just clarify a couple points. So this figure right here is illustrating a general reaction scheme. So we're going to have reactants on this side of the gray line, products on this side of the gray line, and using this stoichiometric method, we can look for different things. We can start with moles on the reactant side and find moles on the product side. We could start with a massive reactant, usually in grams, but it could be in kilograms or something else, and we could find moles of product. We could start with massive reactant and go all the way to massive product. Again, this could be grams or kilograms going to grams or kilograms on this side. So this gray line here is representing the arrow in a balanced equation. Reactants on one side, products on the other side. Now the other thing I want you to just be clear that you don't get confused about is these arrows are all pointing in this direction. We could just as easily go in the opposite direction. In other words, we could have moles of product and figure out how many moles of reactant we had. Moles of product going to mass of reactant, mass of product going to mass of reactant. All right, so depending on how the problem is worded, we can either be going from reactants to products or we can be going products to reactants. When can we do this? The only time we can do this is when we have a balanced equation. So once you have a balanced equation, now any one of these combinations is possible to us. All right, so let's start with a kind of simple example. And here's sort of a typical word problem that you might have. How many moles of carbon dioxide are formed in the combustion reaction of 125 grams of propane, C3H4 molecular weight equals 44 grams per mole, burning in excess oxygen? All right, so what's the first step we need in every one of these problems? We need a balanced equation. So remember, combustion reaction is organic stuff, which would be C3H8 plus oxygen yields carbon dioxide plus water. That's a general form of a combustion reaction. So if you want to write the balanced equation down, stop the video and we can check it in a second. Okay, I'm going to balance the equation in real time. Okay, so I'm going to balance the equation in real time. We'll start with our reaction. C3H8, it's actually a gas plus some unknown amount of oxygen, also a gas, yields CO2 gas plus H2O gas. Okay? Remember, this is a combustion reaction, so that means some organic thing reacts with oxygen to form CO2 plus water. That's a generic form of a combustion reaction. Okay, and now we need to balance the equation. And if you remember the rules we talked about last time, look for terms that occur on both sides of the equation but only occur once. So carbon's a good example of this. Hydrogen is another good example of this. Oxygen is the last one you want to balance because that occurs twice on the product side and only once on the reactant side. So start with the ones that only occur once. Okay, so we got 3 carbons right here, 1 carbon right here, so we're going to need a 3 out in front of the CO2. We've got 8 hydrogens right here. We only have 2 on this side, so we're going to put 4 hydrogens on this side. We'll do a little accounting right now. C3H8O2 on this side, C3 on this side, H8 on this side, and oxygen on this side. We have 6 plus 4. We have 10 oxygens on this side, so this is going to need to be a 5. All right? And now we have a balanced equation. Now that we have our balanced equation, I've erased some of the marks I made before. Now that we have our balanced equation, you want to look really carefully at these problems and see what exactly is it asking for. So how many moles? All right, that's what I'm trying to get at. So I've got moles and I've also got CO2. And what do we know about CO2? Well, we know that CO2 is a product. So going back to our prior picture, that's this case or this case right here. We're trying to get to moles, not to mass. Are formed in the combustion reaction of 125 grams of propane. That is starting with mass. So it's actually the second case example that we're looking at here. We're starting with a mass of reactant and we're trying to get moles of product. All right, so again, solving all these types of problems, we look for the one parameter that is not changing. The one that's given, 125 grams of propane, happens to be our example, and we're trying to get to moles. So we're going to start our problem with 125 grams C3H8. And if you look at our prior example, we want to go from grams to moles. Moles are what allows us to switch from one product to another. So this is going to be 1 mole C3H8 for every 44.1 grams C3H8. You should always cancel these units out just to make sure you're on the right track. All right, now we have moles C3H8, and now I want to convert to moles CO2. So So it's going to be 3 moles CO2 for every 1 mole C3H8. Where did that come from? That came from the ratio here. There's a 1 out front here, and there's a 3 out in front of the CO2. So remember, this term is what allows you to switch from one factor to another. Here's the analogy I like to use. If you've ever been to a city like, let's say, Washington, D.C., and you know there's different train lines. There's the red line, there's the orange line, there's the blue line, and there's only certain places that you're allowed to switch from one train to another, where these are called the transfer stations. You can be on the red line, and there's only a few subway stops where you're allowed to switch from one train to another. Those are the transfer stations. That's what this mole ratio is like. It is the transfer station that allows you to switch from one type of species to another. So we're switching from C3H8 to CO2 with this step. Now, if we go back to our problem, we're trying to find moles CO2. Well, this is going to give me moles CO2 because when I cancel, those are going to cancel out and I'm going to have moles CO2 left. All right, so if I do this calculation, this comes out to be 8.50 moles CO2. Let's just double check our sig figs. There's 3 sig figs with 125 grams. There's 3 sig figs with a molecular weight. So my answer should have 3 sig figs. Okay, so this one comes out to be 8.50 moles of CO2. All right, so I've said this 3 times now. I'm going to say it again. Key point is this step right here. This stoichiometric ratio allows you to switch from one species to another. So we always need to be in moles, which means if we have mass to begin with, we're going to have to convert to moles of our starting thing, and then we're going to switch to moles with this transfer station. All right, let's take a look at another example problem. Okay, this problem's a little more involved. If we look at the question, how many grams of nitrogen are formed in the reaction between N2H4 and N2O4 if we start with 23.15 grams of N2O4? Note, all the reactants are used and the final products are N2 and H2O. Okay, so this is a reaction. We don't have the balanced equation given to us. This is not a limiting reagent problem. This one, we used all the reactants and all the final products are N2 and H2O. So let's begin with the balanced equation. If you want, this is a good time to stop the video, see if you can write the balanced equation down. Okay, here we have the framework of our equation from the wording up above. Remember, we have N2 and N2H4 as one of our reactants, N2O4 as another one of our reactants, forming nitrogen and water. Okay, so there's the framework. It is not balanced at this point, but those are the species that we have. And remember, the other thing that we said is we want to identify the things that only occur once on either side of the equation. So nitrogen is once on the product side, but it's twice on the reactant side. That's the last one we want to balance. Hydrogen occurs once, oxygen occurs once on this side. We can balance either of those first, but the nitrogen's the last one we want to try balancing. Okay, so let's start with the hydrogen. Why not? 4 on this side, 2 on this side. So we're going to need a 2 out in front here. Oxygen, we have 4 on this side. We only have 2 on this side, so I'm going to have to bump this up to a 4. 4 hydrogens, 8 hydrogens. Now I need to put a 2 out in front here. So now let's do a little accounting. We've got hydrogen, we've got 8. Oxygen, we've got 4. Nitrogen, we have 4 plus 2. We have 6 on this side. Hydrogen, we have 8. Oxygen, we have 4. And nitrogen, we have only 2. So if I put a 3 out in front of here, I should now have a balanced equation. Okay, our equations are balanced, which means now we can do one of these stoichiometric reactions. And if we look at it and look at the type of problem that it is, we notice we have mass of one of the reactants, 23.15 grams of N2O4. That's this guy right here. And we're trying to get to grams of nitrogen. All right, so the type of problem that we have is mass of reactant trying to get to mass of product. I'm trying to find that mass on the product side. So going back to our prior picture, it's mass of reactant going to mass of product. It is this 4th type of problem. So we're going to have to convert to moles of reactant, moles of product using my stoichiometric ratio, and then mass of product. Now, if you look at the problem, you notice it does not have the molecular weights. So if you want to stop the video and take a minute or so to calculate the molecular weights of everything. In particular, we need N2O4 and nitrogen in order to finish this problem off. Okay, so let's start our calculation. I've calculated the molecular weights. They're over here. So we start with N2O4, and we know we have 23.15 grams of N2O4. I need to convert this to moles. So this can be times 1 mole N2O4 for every 92.02 grams N2O4 times, now we need the stoichiometric ratio. We're gonna switch between one species and another. So now I need 3 moles nitrogen for every 1 mole N2O4. It's really good practice to cancel out units so you know what's left. And now my last step can be 28.02 grams N2 for every 1 mole of N2. Moles of nitrogen will cancel moles of nitrogen. If we do this calculation, this comes out to be 21.15 grams N2. If we want to check and look at sig figs, I've got 4 sig figs on the N2O4, 4 sig figs on the molecular weights, so my final number should be 4 significant figures. Okay, the next video will be what happens if we have too much of one thing compared to the other. So going back to my earlier example, what happens if we don't have the exact right amount of stuff? I mean, all the examples I've given you so far, all of them, the pizza example as well as the chemical examples, I have exactly 1 crust for 4 ounces of sauce to 2 cups of cheese, yielding 1 pizza. And the chemical problems had exactly the right amounts of reactants in order to form the products. But you know that's not the case. If you go into your closet, you might look up and find, well, I've got 1 crust, but I actually have 8 ounces of pizza sauce, and I have 6 cups of cheese. How many pizzas can I make? Or if I have 10 crusts, but I only have 8 ounces of sauce, then I'm not going to be able to make 10 pizzas. I'm only going to be able to make 2 pizzas. If I have this situation, that's called a limiting reagent problem, and that's what the focus of the next video is going to be on. How do we deal with a situation where we don't have the exact correct amount of stuff to get my products?